Okay, so hello ladies and gentlemen, hello everyone, and please welcome to the presentation of my project, which is about B0 field mapping with dual echo sequences. In fact, it is with dual gradient echo sequences. And as you may know, my name is Gökhan Arıtürk from the EE department. Okay, so let's start. Actually, I will start with the purpose of the B0 mapping method, what it is actually used for. Well, first of all, I need to say that it can be used for viewing the B0, the static gradient, not gradient, the static magnetic field inside the object to be imaged. Well, actually, considering the Larmor relation, we can also say that we can image the resonant frequency distribution, in the spatial resonant frequency distribution inside the object. And another purpose of this can be said as stated as viewing the inhomogeneities of B0 to comment on the artifacts. For example, the bending artifact of SSFP is caused by the inhomogeneity in the static magnetic field, the B0, and we can also comment on that one by having a B0 map inside the object. And also, for the susceptibility case, it is about also magnetic fields. We can also comment on the susceptibility of spatial susceptibility distribution inside the image, inside the object to be imaged. Okay, so I'm gonna state the procedure actually. In fact, how is it done? Well, in fact, there are many different techniques with also different sequences used. One of them is the gradient echo, GRE, and the other one can be viewed as EPI, the echo planar imaging. Well, in my project, I will be considering the dual echo, the dual gradient echo method. And we can say that it is based on the evolution of the image phase between two consecutive GRE executions. More on this later actually, and later is here as you can see. So here we see the pulse sequence for the B0 mapping technique. And actually, in order for B0 mapping, we need two different GRE sequence executions. First with the TE1 and second with TE2, as you can see. But the other parameters are totally same between these GRE executions. And we are considering the phase of the complex MRI image, as I stated. In this, after the second execution, the phase difference between two images is shown by this formula: delta phi equals gamma TE2 minus TE1 delta B0. And as we play with that formula, we can see that delta B0 is equal to this one. And from the Larmor relation, we can also say that the delta F inside the image is also related to delta phi. But keep in mind that this is not B0, this is the delta B0. This is actually the deviation from the nominal value of delta B0 or the resonant frequency. For example, 3 Tesla for B0 and 108 megahertz, 128 megahertz for resonant frequency. Well, I will explain this one in a later slide. Well, in the case of B0 mapping, there's a common problem which is called the phase wrapping problem. Excuse me. The phase wrapping problem actually occurs by the term delta phi in the previous equations. And as we consider the delta phi, it is found by this formula with the arctangent operator. Well, as we consider the arctangent operator, it gives the results in minus phi and minus pi and pi interval. And if the phase goes beyond pi and beneath minus pi, the phase is actually wrapped to the equivalent inside this interval. And here you can see the actual phase and the wrapped phase. And here you can see the sample images of the phase data. This is the difference of those phases, and actually there's a problem with in the transition between these two regions. In order to get rid of the phase wrapping, there are three different techniques or algorithms. The first one is the separate channel method. In this method, actually the data coming from the channels is not merged. They're considered separately, and the phase coming from these ones are unwrapped with an unwrapping algorithm and then subtracted. It's a simple one. And for the phase matching method, which is a different method actually, well, there's a phase offset value defined by theta rx, and this one is determined such that when it is multiplied with the exponential terms, such as this one, the phase of these signals S1L and S2L, there should be an L here, these are actually inside the interval which is minus pi and pi, but beware that the angle, not the actual, these ones are inside the minus pi and pi interval. And then we're just basically moving the phase inside this interval and subtracting it. And also in this method the channel merging procedure is also applying. And the last one is the Hermitian product method. Well, in the Hermitian product method, actually this one I'll be using for the project. Here actually this is for the project. And for B0 mapping, the phase image with the second phase image and the conjugate of the Hermitian of the first phase image is multiplied, and this can be summed over the channels to get the merged channel data. This is a simple one, but this is a very effective one in unwrapping the phase. But as I said in the previous slides, there's a problem, and not a problem actually. We are getting the delta B0 and delta F distributions inside the object, not the B0 and F distributions, as you can see. Well, what does that delta mean? Well, this delta actually means that is referred to the deviation from the nominal value of 3 Tesla, for example, this one. And if it is 3 Tesla, this is 123 megahertz. And if we get the original B0 inside the object, then we need to add the nominal values to the deviations. But in my experimental results, as you can see, I'm just considering the deviation, not the original B0 values. Well, for the experiments, I actually used an agar phantom, which is prepared by 20 grams per liter agar, and this one copper sulfate, and 2 grams per liter of salt. And these are the MR scanning parameters, as you can see in here. And here in this one, the actual results of the B0 mapping is shown by this figure actually. In A, you can see the magnitude image of GREs, one of those GREs, actually the first one with T 6 milliseconds. And the second one, the B image, is the phase image of the GRE with TE equals 6 milliseconds, and this one is the phase image with TE equals 10 milliseconds, and this one is the B0 map. Well, actually this one is calculated with the Hermitian product method, as I suggested, or as suggested by the others, and the other articles actually. And here you can see there's a very little phase wrap. Just here there's a phase wrap, but however there were too many phase wraps inside here. For example, it goes beyond here and wraps here, wraps again, but here just a single wrap. Well, actually after the phase difference operation with the Hermitian product, there can be even unwrapping operation, but I didn't do it, and this is the B0 deviation inside the object. And that's all for my presentation, and thank you for listening actually.